Morning, everybody. Wish you could be here. This is going to feel a little strange, talking math all by myself here, but we're going to give it a shot and see how it goes. We're going to keep things pretty simple to start with. I'm not going to try and introduce too many other things, just to see how it goes from my end and see how well you guys can pick up what's going on. So we're going to give it a try. All right, so today what we're going to do is we're going to get ourselves started on section 8.2. Before the long break now, what we had done was we introduced everybody to sequences and series. Sequences, again, just a collection of terms that follow some sort of rule. And then series, which were the sums of the terms of those sequences. So today we're just going to look at a specific type of sequence and series. That's called arithmetic. And an arithmetic sequence follows a specific rule. And the rule for an arithmetic sequence is a sequence in which the difference between consecutive terms is constant. So an arithmetic sequence is a sequence in which the difference between consecutive terms is constant. So please notice the word difference there. So I could give you some very easy examples of arithmetic sequences. So here's a couple, 5, 8, 11, 14, 17, and so on is an arithmetic sequence, because no matter which term you look at, as an example, if you were to look at the 14 and subtract the term that comes before it, using the word difference, so subtract, the difference between these two terms is 3. If I look at the terms 11 and 8, the difference between those two terms is 3. 8 and 5, the difference between those two terms is 3, and so on. So we say the difference between any two terms is constant. 17 minus 14, 14 minus 11, 11 minus 8, 8 minus 5, all of those, the difference is 3. All right, here's another example. 9, 5, 1, -3, -7, and so on. Also arithmetic, because the difference between any two terms is constant. -7 minus a -3, or -3 minus 1, or 1 minus 5, or 5 minus 9. All of those differences are -4. So whenever the difference remains constant, then what we have is an arithmetic sequence. All right, another example, one that's a little bit tougher to see. So 1, 7/6, 4/3, 3/2, 5/3, and so on. This one's not nearly as obvious, but you take a look at any one of the terms. So let's use our lightsaber. So take a look at 5/3 and subtract the term that comes before it, we get 1/6. Take 3/2 and subtract the term that comes before it, we get 1/6. 4/3 minus 7/6, or 7/6 minus 1. All of those give us a constant value of 1/6, therefore arithmetic. The fourth example is going to be one that's not arithmetic. So this is actually going to be no, but just to get you an example of something that doesn't work. So 1, 4, 8, 13, 19. This is not arithmetic, because if you were to take 19 minus 13, the difference is 6. But then 13 minus 8, the difference is 5. Not the same common difference, therefore not arithmetic. And you could keep going. 8 minus 4 is 4. 4 minus 1 is 3. So the differences between these terms is not the same. So the difference here 3, here 4, here 5, here 6. When they're not constant, it's not arithmetic, it's something else. All right, so we have 3 examples of arithmetic sequences and 1 example of something that is not. All right, now for any terms that are, for any sequences that are arithmetic, we are always going to be looking for that common difference between those terms. All right, and the letter we use to represent this common difference, right? Common means stays the same, difference means we were subtracting. We use the letter D to represent that. So back to my first example, 5, 8, 11, 14, 17. The common difference is 3. Take any one of the terms, subtract the one that comes before it, we always get 3. My second example, take any one of the terms and subtract the one that comes before it. So no matter what you pick, -3 minus 1, 1 minus 5, 5 minus 9, we always get -4. And as we have already said, the third example, the common difference is 1/6. Okay? So those are some examples of arithmetic sequences. Now what we'd like to do is take one of our arithmetic sequences. As an example, the first one, which again was, let me back up, that was a 5, 8, 11, 14, 17. I think I wrote that down okay. So that was our first example. Again, there the common difference was 3. Taking any one of the terms and subtracting the one that comes before it. Now, what we can do with an arithmetic sequence then is we can make a jump from, let me pick my laser pointer here, from the first term, 5, second term, 8, third term, 11, fourth term, 14, fifth term, 17. We could then make a jump to any term in the sequence at all. So we'd like to maybe make a jump from the first, second, third, fourth, fifth term. Maybe there's a situation where we'd want to make a jump to the 20th term, or the 120th term, or the 3000th term in the sequence, all right? And we'd like to know how to get to any of those terms. And to do that, we have a formula that's developed from the arithmetic sequences. And this will be an important one that I need you to highlight in your notes. And it looks like this. To get to any term in a sequence, we call a sub n. So n could then be represented by 20, or 120, or 3000. This value of n then can be represented by, or n can then represent any number you wish. What we do is we take the very first term in the sequence and add n minus 1 multiplied by d. So a sub 1 is the first term in the sequence. In our example, that's a 5. N is the term number we're looking for, so we'd have to subtract 1 from that. And then we have to multiply by d, which is the common difference. So as an example, to apply this formula then to finding the 20th term, to find the 20th term then we take the first term, which is a 5, plus the value of n minus 1. Now since we're looking for the 20th term, the n value is 20, so we'll have 20 minus 1 multiplied by the common difference. The common difference, again, we've already said is 3. So when we do the arithmetic there, 20 minus 1, of course, is 19. Multiply first, add second. 19 times 3 is 57, and 57 plus 5 is 62. So the 20th term in this, the 20th term in this sequence then would be the number 62. If we were to find the 120th term, what we have to do is start at the very first term, then add the value of n, 120 minus 1, multiplied by the common difference. And again, just doing the arithmetic, 120 minus 1 is 119. then 119 times 3 is 357, plus 5 is 362. And let's do one more while we have it up on the screen. To find the 3,000th term, we would take the first term in the sequence, add to that the term number we're looking for, 3,000, minus 1, and multiply by the common difference. So again, subtract inside the parentheses, just doing our PEMDAS. So 3,000 minus 1 is 2,999. 2,999 times 3 is 8,997, and then add 5. And our 3,000th term then is 9,002. Let me clean that up a little bit so it's a little easier to see. Use a little deluxe eraser action there. So what we'd have then is 9,002. Alrighty. And so this formula at the bottom of your screen currently is one that allows us to jump to any term in a arithmetic sequence, right? Whether it's the 20th term, the 120th term, or any term you wish in line, you can use that, apply that formula to get to that term. Okay, let me get you another example of applying that formula just so you have two to look at. So let me get you another, excuse me, another arithmetic sequence. So 2, 9, 16, 23, 30. As you're taking a look at that, just ask yourself, is that going to be arithmetic? What's the difference between any of the terms? If you take 30 minus 23, 23 minus 16, 16 minus 9, 9 minus 2, what do we get no matter which ones we pick? We get a common difference of 7. Taking any one of the terms, subtracting the one that comes before it, we always get the same value, 7. Therefore, arithmetic. And since it's arithmetic, we can then use our formula above to calculate any term in the sequence. So just for the heck of it, let's find a relatively small one like the 40th term, and let's jump up to one a little bigger like the 115th term. All right, just picking two terms somewhere down the road. Okay, so for the 40th term, what we need to do is we need to start with the very first term in the sequence, A1, which is a 2. Then add to that the value of n. The value of n is 40. Subtract 1 and multiply by the common difference, which is 7. Again, just doing PEMDAS in the correct order. 40 minus 1 is 39. And then we just simply have to multiply 39 times 7 and add 2, and we'd get 275. Or to find the 115th term, we start with the first term, which is a 2. Add to that the value of n minus 1, multiplied by the common difference. 115 minus 1 is 114. So 114 times 7 plus 2 is 800 right on the nose. Okay, so again, just an example of applying our formula for an arithmetic sequence to find any term in that sequence itself. Okay, now what we'd like to do is like to challenge you just a little bit. What we'd like to do is, given an arithmetic sequence, we'd like to ask you to find the formula, or if you prefer the word equation, for the sequence. Now, we had done this back in section 1, but in section 1 it was quite difficult to try and figure out how to find the equation of the formula from the terms in a sequence. It was actually pretty difficult, but here it's going to be much easier. As an example, if I were to give you a sequence like this, 23, 32, 41, 50, 59, and so on, and ask you to create the formula or equation that would give us these terms, meaning if I were to replace n with 1, I get out 23. Replace n with 2, I get out 32. Replace n with 3, get out 41, and so on. Can we actually come up with the formula, the equation that does that for us, right? Again, back in section 1, very difficult. Well, at least not obvious all the time, but here much, much, much easier. Watch what happens if I begin with our formula for the terms of an arithmetic sequence, and watch what happens if I just simply replace a sub 1. If I replace a sub 1 with what it's equal to, a sub 1 is equal to 23. And please notice what happens if I replace d with the common difference. And again, how do we find that common difference? We take any one of the terms in the sequence and subtract the term that comes directly before it. So as an example, if I were to take the 41 and subtract the term that comes before it, we get 9. So I could replace d then with 9. And if I do just a little bit of simplifying, watch how easy this is. Multiply 9 times n, 9 times negative 1, and combine the two like terms. What I get then is the formula for a sequence, a sub n equals 9n plus 14. And you can notice now that if you were to replace n with, let's see, let me choose a different, this might work a little better. So if I were to replace n with 1 in my formula, now 9 times 1 is 9, plus 14 gives me 23, the first term in my sequence. Replacing n with 2 in my formula, 9 times 2 is 18, and 18 plus 14 is 32, the second term. And you can see that it works for any of these. Let's jump to the fifth one. If we were to replace n with 5, 9 times 5 is 45, plus 14 gets us 59, the fifth term in the sequence. Okay? So that's one of the questions you'll see in your assignment, is we'll give you some information about an arithmetic sequence, and we'll ask you to find the equation or the formula for it. Okay? Now this one, not so bad, not too bad to do. Now I'm going to scroll the screen up a bit, ask you for the exact same, or I should say, ask you to follow the same instructions. Find the formula or equation for the sequence. I'm just not going to choose to write down all of that again. But this time, instead of giving you the terms of a sequence, instead what I'm going to do is I'm going to tell you the 8th term of a sequence, and I'm going to tell you the 12th term of a sequence. And again, what I'm going to ask you to do is, I'll just abbreviate it, find the equation. So how would I find the equation for this sequence given these two pieces of information? And at first it seems like it's not possible because, again, starting with our formula, a sub n equals a sub 1 plus n minus 1 times d, it seems like it's not possible because we don't directly see the value for a1 and the value for d. We don't see these two values as we did in the previous example. We don't see those values built in to the information given. We're told that the 8th term is 25 and the 12th term is 41. So how are we expected to be able to get to the equation? Well, the answer is we actually apply the formula itself to a sub 8. So we take this piece of information, a sub 8, and we apply the formula. So in other words, we're saying, well, if we use 8 specifically for the value of n, a sub 8 would be equal to a sub 1 plus 8 minus 1 times d, right? Just replacing n with 8. Well, the nice thing is we actually know what the 8th term is. We know the 8th term actually is 25. Now, I do not know what the first term is. I do not know what a sub 1 is. Of course, I could subtract 8 minus 1, giving me 7. But I also do not know what d is. So just replacing the 8th term with 25, you might think, well, that doesn't do anything for me because, what I have is one equation with two variables. One equation, two variables, bad, can't solve. But if we do the same thing for the second piece of information, that a sub 12, the 12th term, is 41, watch what happens. So if we use that piece of info, the a sub 12 is equal to a sub 1 plus the value of n minus 1 times d. Oh, well, we can actually replace a sub 12 with 41. Of course, 12 minus 1 is 11. And again, we get one equation in two variables. But what works out really well is, if I slide this fella over, by doing that with both pieces of given information, now I end up with two equations in the same two variables, and of course we can solve that. I'm just going to simply use elimination. So if I was doing this one on my own, I would leave the first equation alone, and then multiply the second equation through by -1, so 25 times -1, a1 times -1, and 7d times -1. And when I combine the equations, the a1's cancel. 41 minus 25 is 16, and 11d minus 7d is 4d. So dividing both sides by 4, our d value then is 4, right? And now if I back up to one of the equations, and I'm going to choose this fella right here, I could now replace d with 4. Now I can replace d with 4 because I found that value. And now that leaves me with a1 to solve. So 7 times 4 is 28, and move 28 to the other side by subtraction. So I now know a1 is -3. So now, after all of that work, now I can go back to where I first wrote down my formula, a sub n equals a sub 1 plus n minus 1 times d, and replace, just as we did on the previous example, a1 with what it's equal to, and d with what it's equal to. Again, a little bit of simplifying. Distribute a 4 times n, 4 times -1. What we'd get then is a sub n is equal to 4n minus 7. And again, we have a formula then, or an equation, for an arithmetic sequence, which would give me the 8th term being 25 and the 12th term being 41. And if you wanted to, you could test that by replacing n here, right here, with 8. 4 times 8 is 32. 32 minus 7 is 25, the 8th term. Or replacing n with 12. So 4 times 12 is 48, and 48 minus 7 is 41. There's the 12th term. Okay? So again, there's going to be a few examples in your assignment that'll ask you to work with some information like that to find the formula, the equation for an arithmetic sequence. All right, I'm going to take a little break here. I'm going to try to upload this video. There is going to be one more video that follows that will have a discussion which changes from now looking at arithmetic sequences to arithmetic series. So I'm going to pause this video and try and get it downloaded and see how it works. But expect that there's another one that will finish off the rest of section 8.2 dealing with arithmetic series. All right? Hope you're having a good time. It is math class, so hope you're loving it.